go ahead and start with an example. This is problem 33 in your chapter, and we have a plank sitting on a fulcrum, otherwise known as a teeter-totter or a seesaw, and we have a child sitting on one end and a child sitting on the other end, and because of the way this is set up, the center of mass of the system is balanced on the fulcrum and everything is in balance. In other words, we're static. And we know the mass of the object on this side, we know the mass of the object on this side, and the question is, if we know these distances, so we know that distance and we know that distance, the question is, what is the mass of the plank? And if there was a massless plank on there, then the center of mass would be balancing these two masses. But because there's some non-zero mass for the plank, we have to figure that out. And we're going to consider this to be a uniform plank. So we can imagine the center of mass to be right here for the plank by itself. Okay, so we identify our system. Our system is going to be this plank and the two children on board, and we're going to first start with the forces. So we're going to start with identifying the sum of the forces, and the sum of the forces are going to be equal to 0. Now there are no forces in the x direction, so we don't have to worry about that. So let's go ahead and draw our forces in the y direction. We have the force due to gravity of the acting on the child A. We have the force due to gravity acting on this child B. We have the force in the middle here, in the force due to gravity acting on the plank. Call that MP. And then we have the fulcrum point here, and there has to be a normal force pointing up like that. That has to be the normal force on the plank. We'll call that, we'll just call that N. So those are our forces acting, and because everything's in balance, the forces that are pulling down have to equal the forces pulling up. So just putting signs in these, I can say that the normal force of the whole system has to be positive because it's pointing up, and then we have the gravitational force of child A minus, call that MPG, the gravitational force of the plank minus the gravitational force of child B, and that all has to be equal to 0. And that means that this normal force is just going to be FA plus MPG plus MFB. Plus FB. Okay, so if we look at this, we can rewrite the gravity here as MAG. We can write the gravity here as MPG again, and we can write the gravity here as MBG. Now you'll notice here that we don't know what this normal force is, and we don't know what this mass of the plank is. So just doing the forces isn't going to get us there. Okay, we need to deal with the rotations as well. And in fact, in this particular problem, we could do it with just the rotations, but since we've done the force calculations before, I thought I'd start with that. So now let's look at rotation. We're going to draw our system again, and we have our force due to the child on this side, we have our force due to the child on this side, we have our force due to the center of mass of the plank, call that FP, and then we have our fulcrum point, which has our normal force pointing up. Now, like I said before, you get to choose wherever you want the rotation axis to be, and since we don't know the normal force, if we choose our rotation axis right there, then the normal force is not going to be contributing to the rotation around that axis, so we can just ignore it. So in this case, our normal force times the distance from our axis of rotation is going to be 0, right? So you know what this is. That was given to us as 3 meters. We'll call that RA. We know what this is because that was given to us as 5 meters. And since we know this plank is uniform, we have 8 meters across. So this is going to be 4 meters, which means we know this distance here is 1 meter because we can just subtract 4 from 5 to get 1 in that position. Okay, so now we look at the rotation here. The torques on these is going to be the force crossed into the distance, or the distance crossed into the force. And that cross product, though, because we have 90 degrees in each one of these cases, is just going to be the product of the force times the distance away. We have to worry about the direction of rotation here. And again, I use my right-hand rule. And if a force is going to cause the object to pivot in the counterclockwise direction, I call that positive, and I use my right-hand rule. So if this is the direction of this sweep is the direction of rotation, that's counterclockwise. So I say that this force that's going to cause it to rotate that direction is positive. So I'm going to say that our sum of the torques is going to be FA times RA, positive. Then we have FP would tend to rotate it the opposite direction, so I'm going to say minus FP RP, and then FB is also going to rotate it in the clockwise direction, so I'll call that minus FB RB. And we just have those 3 forces acting because we can ignore the normal force, and that is all equal to 0. So that's the sum of the torques are equal to 0. Now I'll go ahead and put in things that we know. We know the mass of A, we know G, we know RA, we know the mass. We're trying to find the mass of the plank. We know gravity, and we know the distance the plank is from the fulcrum. And we know the mass of B, and we know G, and we know the distance to B, and that's all equal to 0. So then just solving for MP, I'm going to get MP times G times RB is equal to MA GRA minus MB GRB. I think I did that right. My G's are going to cancel, and that's going to mean that if I divide through by RP, if I divide through by RP, then I'm going to get the mass of the plank is equal to MA RA minus MB RB divided by RP. And before I do this calculation, I'll just check the units real quick. I've got a radius times a mass divided by a radius, so this has units of mass. I'm going to get a positive number because MA is larger than MB, so that's good. And I go ahead and put in my numbers here. MA was 80 kilograms times 3 meters minus 40 kilograms times 5 meters divided by 1 meter. Again, the units cancel for meters, and I'm going to get 240 minus 200, or 40 kilograms for the plank. And then for my significance, I think just kind of thinking about an 8-meter long plank, that's 40 kilograms seems pretty reasonable. So this seems reasonable given size of plank.